and I work as assistant professor at the GIKI Institute of Engineering Sciences and Technology. And in this talk, I will talk about functional programming, what it is, some of its merits that make it desirable, and how you can do functional programming in Python. So, the major theoretical basis of our discipline, computer science, was laid in the beginning of this 20th century, around 1930s, etc. So there were two models developed about computation. One of this, the Turing machine, which was developed by Alan Turing. We encounter it in our courses like theory of automata, etc., which nobody thinks that it's any use, etc. But it's the theoretical foundation of computer science. Okay. All our machines, they operate, they are inspired from this Turing machine. Our dominant languages that we use, they are imperative languages, and they also are based on computers. They are targeting computers which are based on Turing machines. But a fact that is not very highlighted in at least Pakistani education is that an alternative model was also proposed at the same time, which is called lambda calculus. In fact, its inventor, Alonzo Church, he was a close collaborator of Alan Turing, and I think he was even the PhD advisor of Alan Turing. Lambda calculus, it's based on mathematical functions. So it treats functions as unit of computation and proves that you can do any computation by using function calls. In 1936, I think Alan Turing showed that both these models, they are equivalent in terms of expressivity. That whatever computation you can do on Turing machine, the same computation can be done on lambda calculus and vice versa. In our today's, for example, Pakistani ecosystem, we teach imperative languages targeting these computers which are based on Turing machines. So from Turing machine, we derive register-based machines, and the RAM-based model, which is like the von Neumann architecture, which underlies all our processors, is basically derived from or finds its source in the Turing machine. All our languages, the compilers that compile those languages, they are targeting these processors, and our programming methodologies or paradigms, they have their root in Turing machine. There are other languages whose paradigm is inspired from lambda calculus. We call them functional languages. Function, again the word function, because it uses mathematical functions, and they are not mainstream. In, for example, I have taught in Pakistan and even worked in the industry, but rarely have I heard about functional languages or use of functional languages in Pakistan. It was only in Habib University that I heard that they taught a course on functional data structures. But the functional languages, they exist in the industry. These are some of the languages. I don't know how many of you have heard the names of these languages. Scala is a functional language. But you see, they are not as familiar as C++, C, etc. Those languages, they are not as familiar to us. But these languages, they find their root in the functional paradigm, and they use functional programming style to develop programs that you can run on these computing machines. So what's functional programming? Basically, it's based on lambda calculus, which takes the mathematical function as a unit of computation. And what's a mathematical function? It's a mapping from input to output. Okay, in our calculus courses or basic mathematics courses, we study that function. It maps a range to a domain. It maps a domain to a range. Okay? The domain is a set of input values that you can give to a function, and it will give you a set of output values. For each input, it will provide a point or a mapping in the output domain. So a mathematical function is not like a computer function that we use in C or C++. The functions that we use in C, C++, and these imperative languages, they are more appropriately called procedures. Procedure has side effects. For pure mathematical function, it does not have side effects. So what is a side effect? A side effect is if a function does something else other than mapping an input to an output. So in pure function languages, functions are pure, which means they don't have any side effects, which means that their output depends only on their input. There is no global variable that they are using to calculate the output. Global variables, are that they create dependencies in your code, which, if there are too many dependencies of using global variables, which makes your code complicated like spaghetti, which is difficult to maintain and difficult to debug. With pure functions, you don't have such dependencies. They don't use any global variables, neither they modify any inputs. So your code is modular, compartmentalized, and if there is a bug or something, then it's localized and it's easier to debug and maintain. Secondly, okay, so no hidden states. So the hidden state is again if there is some like in C++, we have static variable. Static variable is local to a function, but it's like it exists across function calls. It gets initialized on the first function call, and then across the next few whatever function call, it will exist. And if you are using that to calculate your output, then again your output is not only depending on its input. You are using the hidden state, which is again problematic in the sense that it's you can't look at the function call and say how this output is being calculated. Again, it's a hidden dependency that can cause problems and can be difficult to do. And third, function languages have functions as first class objects. An entity is a first class object in a programming language if it can be used just like any other entity. For example, in C, there is no function is not a first class object in C. You can't create a function object, assign it to a variable just like data. You cannot pass it as an argument to a function. You can't return it to a function. C uses a very convoluted mechanism of using function pointers to pass functions to other functions as arguments and return functions. I don't know if anybody has used function pointers in C, but their syntax is like very convoluted, okay? Because it's not a part of the language design. It was like allocated. In function languages, your functions are first class objects, so you can create a normal function just like data variable. You can create a function variable. You can assign value to it. You can pass it to a function as argument and return a function as return value for the function. This provides the ability of using high order functions in a language. A high order function is a function that takes another function as an argument and can return a function. We'll see an example how this can increase your programming expressivity. Third, the fact of returning functions basically helps you implement lazy evaluation. Lazy evaluation is the fact that if a computation is not needed, you don't need to do it. If you have to calculate a long list of prime numbers and you are not sure whether you are going to use all of them in the program, then in C++ or C, for example, they are not lazily evaluated, in C especially. So you have to generate the list of prime numbers upfront. You have to do all that calculation. Even if you, for example, use 5 to 10% of those prime numbers later, you still have to generate all of them at the start, because you don't know which ones are you going to use or how many are you going to use. You don't know that. In lazy evaluation, you do a computation only if you need it. So at runtime, you basically ask the program to generate a prime number, and it will generate only those number of prime numbers that you really need. A third, a last feature of functional languages is data immutability. Since you are doing all your computation using functions, a function can take an input and it can produce an output. There is no notion of variable in lambda calculus, which is the foundation of functional programming. There is no notion of a variable which is a place in memory, and you can go and change that value in that memory. So data by default is immutable. You can't change the value. If you want to, for example, if you want to add an element in a linked list, then your function takes as input a linked list and it returns a new linked list with that new element added. It does not modify the original data because data is by default immutable. So these are some of the properties of functional languages, and we'll see how do they basically improve your programming abilities. So these are some of the functional languages that are used. What about Python? Is Python a functional language? By inception, no. But today's languages, all these major languages, they have a long history. And in those like 30 years of Python or around 50 years of C++, these languages exist in an ecosystem with other languages. Some of them are functional, and these languages like trade features. So imperative languages borrow features from functional languages, and vice versa. Functional languages borrow features from imperative languages. So today's languages are like multi-paradigm languages. Python is one of those multi-paradigm languages in which you can do programming in a procedural way, in an object-oriented way, and also it has some functional features which you can use to do functional style programming if you choose. So one of the requirements of a functional language of doing computation to function is having higher order functions, and for that we need an ability to create functions on the go. So anonymous functions is basically the ability to create functions without any name, which you can pass as values, use them, etc. Python has the ability. If you are using Python, then you must know that Python has lambda feature, which lets you create a function on the go. It's an anonymous function, you don't need to give it a name. Secondly, functions are first-class objects in Python also. It was added later, I think, not from the start, but you can pass function as an argument to a function and return a function from a function. So Python has higher order functions. And secondly, in a way, Python also has immutable data. If you make your data a tuple is immutable. So to do like functional programming through and through, you have to do your data, make your data real immutable. In a tuple, you can have a member of tuple, which is a list, and you can go modify that list inside that tuple, modify part from it. So if you want to do real functional programming, then you have to have tuples all the way down. Tuples, column sets, and things like that, which are unmodified. There are these two modules which are part of the Python standard library, func tools and attributes, which provide you some functional constructs that you can use to do functional programming. So let's look at higher order functions. What are they and how do they improve or increase your programming expressibility? Let's consider this function, this one. This is a function which is basically doing the summation of natural numbers over an interval. So from 0 to n, it is going to sum all the numbers. We can have other functions which are doing same kind of thing. This is another function which is basically operating over an interval, but this time it's instead of summing numbers as they are, it's summing or doing a summation of the cubes of those numbers, n cubes. This is another function which is also operating over an interval. Basically, this is an infinite series which converges to pi. So we can go get a good approximation of the value of pi by doing a summation of these terms over a certain interval. So again, this is operating over an interval and it's adding these terms over that interval. So what's this term? It's 8 divided by n multiplied by n plus 2. Again, n multiplied by n plus 2. So if you look at these functions, they are basically operating over an interval and they are adding terms over that interval by applying a certain function to each element of that interval. Here we are just adding the number as they are by applying an identity function. Here we are basically applying a cube function before adding the terms, and here we are basically converting the point of the interval into this term before adding. So how can we capture this general pattern? Otherwise, we will have to define for each type of summation, we will have to define a separate function. What a higher order function does is that it basically captures this idea of summation. So we can basically do a summation over an interval, and the exact function to apply on each point of that interval. How to produce that term? We can pass it as a function. When using this summation, we can basically pass it a function which will generate the appropriate term, whether it's identity or a cube or that term, and then basically after generating that term, it will move to the next point in the interval. Again, the next point can be we can either increment by +1, or for example in this the pi series it was a +4 of a difference. So again, since that's also changes from function to function, so we can pass that operation of going from one point of the interval to the next point also as a function. So if we define this notion of summation in this way, that we have sum numbers over an interval by applying this function to each point in an interval and then going to the next point in the interval, we can rewrite all the preceding functions as this summation function. For example, if I have this function successor, which basically increments to go to the next point in the function interval, and then this identity and this cube function, which basically when applied to point in interval, identity basically returns at the point as it is, and cube basically returns the cube of the function. Then sum of the natural numbers would just become a summation by applying identity on this interval, okay, and then using this function to go to it. Sum of cubes would become again a summation by applying a cube and going to the next point in interval by applying this successor. The pi thing again, if I can, this function, which if I pass it the point, it will generate this term for the series, and for the next we jump maybe for 4. Again, we can calculate the value of pi over an interval by passing it this function and the successor function, how to go to the next point in interval. So this summation function, we can use it to capture this action of summation over an interval for doing any kind of summation. Okay, so it basically, instead of generating a separate function for every type of summation that we want to do, we have basically captured the general concept of summation, and what particular summation we want to do, the user of the summation can basically pass it the appropriate function, and basically they can perform summation. So PyCon, these some tools that we func tools and iter tools, these are PyCon modules which provide you these higher order functions which you can use to do function style programming in PyCon. So we have map filter reduce, which we are going to see, and then we have these features of PyCon like decorators, closures, etc., which are enabled by using higher order functions. So map reduce filter, if you have already used them, basically map takes an iterable and a function. So it will generate another iterable as a result, and that iterable will be generated by applying this function to every element in that iterable. For example, if I want to double every element of this list, I will pass it this iterable list and then pass it this lambda anonymous function, which it will apply to each element in the list and give me this list. Again, this is possible only because of having higher order function Python. Filter again applies this function to every element in the list, but filter expects this function to be a predicate. A predicate is a function which returns true or false. Okay, so it will only keep those elements in the return list which have true value for this predicate. Again, it takes a lambda, and you can see that it basically creates a new list. So these follow the function principles of immutable data. Do not modify the input. Reduction again is an operation which you can apply a function repeatedly to condense a list into one single value. For example, addition, we can apply on this list to reduce all these to one single value, which is the sum of all these numbers. If we have these functions in our toolkit and we think functional, then we can basically arrange our algorithm or program to come up with a better design which is easy to understand and maintain. For example, let's say I want to calculate the sum of even Fibonacci numbers up to an interval, like between n Fibonacci numbers. I want to select which ones are even and then sum them. Suppose I have this function fib, which I give it number k and it returns the kth Fibonacci number. And this predicate is even to test whether it's even or not. If I do an imperative style programming, then I will do a loop over n, and for each n, I will generate the nth Fibonacci number. I will check whether it's even, and if it passes this test, it's even, then I add it to my sum and I accumulate the sum of the even Fibonacci numbers over a period and return the sum. Now here we are doing some certain steps, and in this imperative style of programming, since we are thinking imperatively, we are mixing a lot of things together. For example, in the same iteration, we are doing enumerating the interval from 0 to n. We are basically calculating Fibonacci of n. We are doing predicate testing, whether it's even or not, and summation. So it's all the computation are happening in every iteration, and they are spread over all the iterations. In a functional style, we can use these map reduce kind of things, and basically this range, it will generate an interval from 1 to n, and then I'll pipe this range into this map function. Map, it will take this range and apply the shift function to every element in the interval. This will give you a list of all the Fibonacci numbers, and then I pipe this whole list of Fibonacci numbers into this filter function, which will basically filter all the even Fibonacci numbers from these from this list, and this reduce function sum, it will basically take all the list of those even Fibonacci numbers and reduce it. So here we have clearly delineated different steps in a compartmentalized way. It's like shell programming. In Linux shells, you have these pipe operator. So you basically you just run the first command, it processes data, and then it generates some output, which basically you pipe as an input to the second command. And so the same thing is happening here. So this is generating the interval, which I am piping to map. Map is basically generating Fibonacci numbers, which we are piping to filter, and filter is basically filtering those Fibonacci even Fibonacci numbers, which are piping to sum. Sum is summing them together. Somebody even made this module PyCon library, which is available on GitHub, that you can use Py21 to do the same thing. But again, the notation is shell pipeline style notation, in which all the steps are very clear. Compare this, how neat and clean this design is to do this function where all things are intermingled in the same iteration, and all the iterations, the computation is spread across all the iterations. So in here, I'm basically doing one thing at a time. my code is more modular, and there is no like dependencies across different computations. And let's say since there are no dependencies, let's say I find an alternative map function which is like parallel, for example. So I can just plug in, like Lego, I can just take this block out and plug that parallel map function in, and the rest of the code is not affected. So functionally, basically thinking in functional type, it improves your program design, and your programs are much easier to maintain and debug. So these kind of things are really important when your programs get bigger, and if there are a lot of interdependencies across different parts of codes, then debugging or localizing the bug is very complicated. Again, ideally your functions should be pure. They should not use any internal state. All of these functions map into reduce. They take an input and produce an output. There is no internal hidden state being used. So whenever you give the same input, the function will always give the same output. And the output is solely determined by the input that you provided. This results, thinking like this in functional style results in modularity. And since there are no side effects of your functions, there are no interdependencies across code portions, and your design is modular and easier to debug and localize. And the modules can be replaced whenever you need. Data by default in functional languages is immutable. Here, for example, this function add item, it takes a list and appends an item to the list. This is not functional style. This is modifying its input. So it's basically creating a side effect. Whichever function calls this add item, it will be the change in the original input will be visible to that function or thread. So this has a side effect which is not like desirable in functional objects. For example, if our lists were coming, the list we are getting from this getList function, and this is a thread that is basically going to process add an element in this list, and getList basically returns us a reference which is also being used by another thread. Then this thread is never sure whether somebody would modify this list while it has not finished processing it. So if that list gets modified while this thread is also processing it, so anybody who's done parallel programming with multi-threading, etc., you know that race conditions are when multiple threads try to modify the same piece of data, and race conditions are bad because they corrupt the data and crash the code. Here is another version. This is functional style. It basically is taking the list and returning a new list by adding an element. So whichever thread is basically using that list in another context or another CPU core, that's a separate list. The list that we are getting, that we are modifying in this thread, is a separate list. So with immutable data, you have like threads working on separate copies, and they can be sure that their data is not being modified by something in the background or something that they don't know about. So this, in multi-threaded programming, this is a very useful feature that can result in safe programs with no race conditions, or at least race conditions are difficult with this. So data can be easily shared among threads. So these are some of the modules that provide you capabilities of doing functional programming in Python. Python, as I said, is by default not a functional language. So data by default is modifiable. I think whenever you make a sequence, the default thing that we reach out to is list and not a tuple. So list by default is modifiable and non-functional data. But still, Python basically gives you these function tools and data structures that you can use to do functional style programming in Python. So the first two are like a part of Python style library, and these are like I found on GitHub these modules that you can do functional programming in Python. Python, since it's not a function language by default, so there are some limitations. Lambda syntax is limited in Python, that it can only be a single expression. You can't make a big anonymous function, not big is not recommended, but still a sizable, significant lambda function in Python. You can only use one expression lambda function. To do functional programming, data is immutable, so every change creates a new copy of data. So if you keep creating new copies of data, then it would be like very resource heavy, this program. You will be using a lot of memory. So there are data structures provided by functional languages which call them persistent data structures. In persistent data structures, if you modify an element, a new copy is created, but the new copy shares a lot of the old copy. So in terms of memory cost, you are not much penalized. In Python, persistent data structure is not available by default. You can use third-party libraries. For example, this library, it provides persistent data structure for Python if you want to use them in functional style. And another thing, in Python, it's not a problem. In Python, you have loops, but in pure functional programming, since you are doing all the computation using functions, there are no loops. If there are no loops, how do you implement loops? Because loops are an integral part of program. So they do it by recursion. If you are doing loops for recursion, then it's a lot of function calls. Function calls, as we know, are like costly. So they mitigate this computational cost of calling recursion for implementing loops by doing this optimization, which is called tail call optimization. A tail call optimization is that if the last instruction of your function is a recursive call, the function is calling itself as the last step of its execution. Then basically, instead of allocating stack frame for every function call, which normally happens, you can basically reuse the old stack frame. Because since the last thing that this function is doing is calling itself, then it's not going to need any of the variables that is allocated on this stack frame. So for the new call, instead of allocating a new stack frame, we can use the same stack frame. So this basically minimizes the function calling cost in terms of stack frame allocation, and your recursion behaves just like a loop. But in Python, there is no tail call optimization. Tail call optimization does not exist in there. So that can be. So this was a brief view or introduction to what functional programming is, how you can do functional style programming in Python. We have only seen a couple of examples of how it can improve your program, but if you read up on it, then there are a lot of things that we have not discussed in this presentation, but it basically there are a lot of features which let you operate at a very high level of abstraction, and you can do a program powerful paradigms and functions. So I will leave some time for questions if there are any.
I don't really understand why is it necessary. Yeah. Why is it really necessary to avoid loops within the functional paradigm? Why can't we just migrate to an input? Why do we really have to resolve the question? Because I don't think it makes any sense.
The functional programming is based on lambda calculus. So the question is, why do we need to avoid loops in functional programming, and why can't we have loops in functional programming? Why do we have to use recursion? So functional programming is based on lambda calculus. Lambda calculus has only, it's a mathematical foundation which uses only a mathematical function as a unit of computation. So a mathematical function is just a mapping from input to output. There is no, for example, in mathematical functions, there are no loops. So that's for starters. And another big reason is that in loop, you have mutable data. What is being mutated in a loop. In every loop, we mutate at least one variable. The iterator, the I++. So in functional programming, in pure functional languages, we try to avoid mutable data.
Yeah, but we're like not muting the inputs too. I mean, if you're using an iterator and you're using a local variable, you're still not altering the input.
It is correct that iterator I is a local variable, and you are not creating a side effect outside that function. So first of all, there is a theoretical foundation. For theoretical foundation, you have to have a coherent theory. So if they started with a immutable data concept, like there's no concept of variable in pure functional programming in never calculus. So I is a variable. So they had to have a coherent theory. Right? So this is like an incoherent. But there are some languages which mix different paradigms together. For example, in PyCon, you can use an iterator with functional style programming. And I think there are some, I might be mistaken, but there might be some functional programming languages which use loops. I will refer to my more knowledgeable colleague here.
Scala is used quite commercially as well. Scala is written on top of JVM. Scala may have many non-functional features as well.
Yeah.
I mean, one functional feature, there's no concept of input. That's very strange. There's no concept of input or output in Java calculus. But in order to be useful, these functional languages have to provide input or output. So then they usually have some kind of unsafe category. And under unsafe, you can do input output. You can do IO.
You can't have programs without I/O. It doesn't make sense. Yeah. So since we have to do I/O, so they basically try to have the core of their program in pure functional style, and then where that core needs to interact with the outer worlds, you make a bridge kind of function which basically provides transfer data from outside world to the code and vice versa. So since the mutation or the non-data mutability is happening only at the periphery of this code, so it's much localized. So if there is some bug or some data corruption, you have to focus your attention only on that part of the code. With functional code, you are sure that there is no data corruption in there.
That makes sense. Thanks.
There is a similar thing in Rust as well. If you look into Rust, Rust also is very strict on its memory semantics.
Rust, of course, is very popular these days. It's been like the most favorite language on Stack Overflow for several years running. And the main popularity of Rust is that it's memory safety. But even Rust allows some backdoor where you can do memory unsafe, but then you have to go to some lengths to declare that, okay, now I'm doing something, I'm explicitly, knowledgeably, deliberately doing something that's memory unsafe, and then you return to your memory safe operations. So some kind of workaround is provided there as well.
Assalamualaikum. Thank you for the talk. In the beginning, you mentioned that modern languages, they share features across, like some features from JavaScript might be in common with Python, and some features from Scala might be in common with Python. So in that sense, so do you think it's advisable to stick to just one paradigm of programming, or like in normal practice, we adopt multiple paradigms and picking up what suits us and working with what we have? So like as long as the code works, so do you think it's advisable to stick to just one kind of a paradigm?
I will suggest experimenting with different paradigms and then making an informed decision once you know the pros and cons of different paradigms. For example, I have worked in C++ for a long time, and in C++ exists since 1970s, and it is only in 2011 that they incorporated lambda as a feature. So for these previous 40 years, C++ was without any of those functional features. I was not exposed to functional features until recently. So if I had been in C++ only, then I would have missed these features or this kind of thinking for a long time. So, however, functional programming exists since 1990s. Lisp was the first programming language. I think it's one of the oldest. Only Pascal or Fortran, one of those languages is older than Lisp, which is currently being used today. Otherwise, Lisp is one of the oldest languages. So these notions and these paradigms, they exist for a long time. But which language adapts them at which point in time? So you might, if you stick to one paradigm, one language, then you might not be exposed to all these features until that language decides to adapt these features. These features are not necessarily, if your language does not have these constructs, it does not mean that you can't benefit from these features. If you are exposed to these features and you think in functional style and your particular language does not have those features, you can still try to arrange your code in some manner such that, for example, you can think about the mutation state and try to localize the mutations in the state of your variables to a certain part of the code so that the rest of the code does not mutate anything. So this way you localize the sources of bugs that are caused due to mutation state. So even in non-functional languages you can use these features. So it's better to get exposed to different languages and then make a decision. That's not the point.
I have a question here. So if we have a function that has like let's call it a hook, like it causes some other function to be called. So does that still come under the paradigm of functional programming, or is it like it sort of doesn't remain under that? For example, if we save something to a database using function, and then many ORMs also provide this like a post-save hooks, which are called every time some change is made to the database. So those hooks, are they considered part of functional programming, or sort of it sort of doesn't remain under that?
So before I answer this question, can you please explain how is calling a hook different from calling a normal function?
So I guess the point is, like you mentioned, that there should be no side effects. There should be an input and an output and nothing else happening inside a function. So, but obviously, hook will need to be called before the function returns. So if it's doing something else, then isn't that kind of a side effect?
So if that hook is modifying something beyond that function, like adding a row in a database, then that's a side effect.
Right. So it will sort of divert from the style of functional programming then.
Yes, this will be like making a change, non-local change.
Yeah.
You're not changing anything in this function apart from the output. You're changing something else in some other part of the program.
Yeah.
So that would be a side effect, and that would be like against the.
Is there like a advisable way to manage this kind of situation in a functional way?
I think what Vikas said, that you can try to limit those dependencies in certain portion of the program only.
Mm-hmm.
So try to do as much of your core computation, etc., in functional side, and then there is that non-functional code, which is basically going to cause side effects. And if you can basically separate and compartmentalize that part of the code, then if there is a error or bug, you know that it's being only caused in those parts of the program, so it's easier to debug.
Right. Thank you.
This will be the last question we'll be taking. We're short on time.
Okay, so I'll be here all day today and tomorrow, so.
Okay, first of all, thank you for the presentation. So my question basically has to do with optimization in this functional programming aspect. I understand the modularity and the readability arguments, but like in your example, you showed that first we map over the Fibonacci sequence, we filter over it, and then we reduce it, right? So in the procedural style, when we were just one iteration, it was just one iteration. We were doing everything in that. But when we switched to functional, right, we're making three separate, they're basically recursion, but let's say iteration, right? We go over the sequence 3 times. So isn't that like counterintuitive?
Performance-wise?
So yeah, I mean like isn't that worse in terms of optimization and time complexity?
Yeah, so performance.
Yeah, performance.
So performance, this is one of the main critiques of functional programming languages. Since you are doing lots of recursion and lots of data copying, in case you are data is immutable, so this has a performance cost. But when you have to decide whether this cost will work or not, then in that case, the way I try to answer this question is that in most of our use cases, our modern hardware is powerful enough that performance should be a second thought. For example, the quote that premature optimization is the root of all evil. Once you program your, make a program, and then if it's slow, you measure, and then if you find it's slow, then I think you should go for performance. In 80 to 90% of the cases, I would hazard that the correct working of the program, or the long-term ease of maintainability and debugging, that would be the first priority instead of performance. If you are doing high performance trading, high frequency trading, or like the real-time missile system guidance thing.
Basically, I asked, sorry, interrupting you. I asked this question because I know that Elixir is used in these real-time chat applications and sort of the performance-intensive applications. So how do they get around? Because it's purely functional. So how do they get around this performance limitation? Because
So I think Upa wants to.
If you go back to that slide, the one where you PyCon functions.
So what I was going to say is that it might look like, maybe once the slide comes up, it'll be easier. It might look like, one function completes execution, and then the result is passed to the next function, and that result is passed to the next function, that result is passed to the next function. A good compiler will not do that. A good compiler will treat it like function composition in math, and it will treat the composite. So here, right? So it might look like the result of reduce goes to filter, the result of filter goes to map, and the result of map goes to range, and so on. But a good compiler will not do that. A good compiler will compose all the functions into a single function, which is applied once to each element in that range.
So it will do the imperative thing, but in the background.
Yeah, in a way, so it'll compute a composite function, composite of all of these, and that composite function will be applied to, in a way, it'll like run a for loop. Conceptually, you can think of it as a for loop, which applies that composite function to all the elements each element in the range.
So there are compilers that do backend optimizations. Even the data copying thing, we have persistent data structures in which when you make a copy, it doesn't make the copy of the whole data structure, only the part needed to differentiate between the two. So thank you very much for your participation, and I'll be here if anybody has any other questions.